You are muted, sir.
Sir, you are not audible, sir.
Sir, it is not audible, sir.
Sir, no voice.
सर आपकी आवाज नहीं आ रहा है।
Recording in progress.
So even though people kept calling me because my phone was switched off, so I did not notice. It never happens that at the time of joining, I forget clicking on that join with computer audio, but it's just the first time it happened. Luckily, I did not teach anything new so far. Conditional probability is something that we have anyway studied. Ramanujan Bose. So those conditional probability we know now. A given B multiplied by B. That also you can write A intersection B. B given A multiplied by A. That also you can write A intersection B or B intersection A. Now, since A intersection B and B intersection A, they are the same things. So if they are the same things, I'm just going to A intersection B and B intersection A, I'm just going to equate them. And once I equate them, I'm going to get this result. Make a note of this result. This is a very important result, and we are going to make use of this result in today's class. Make sure that you make a note of this result. This is rather important result, okay? A very important result. But before we start watching class first time while traveling in train from college to home, actually while traveling, if internet connectivity keeps supporting, watching classes with your earphones plugged in while traveling is one of the best thing to do. For one whole semester, I did my entire study in bus. In whole of my third semester of BTech study, the whole semester I studied at my 90% study was completed at one place while traveling in a bus. Cool. So that helps you focus very, with a lot of intensity. Anyways, so this result, make a note of it. We are going to need it. We are going to use it. And my dear friends, whatever we are studying, it's not a separate thing, but it's actually a wall being built, probability 3.0. And this was just a brick of the wall. This was just a column of the building. We are going to build on this column. Don't worry. Let me go ahead and introduce you to the next important thing. And the next important thing, again, we will try understanding through problem only. Tell me the score, people. Somebody please tell me the score. Go ahead.
22, sir.
22nd. Okay. So here we go with the 22nd. And as a 22nd problem, let's say we have, as a 22nd problem, let's say we have, okay, let's take this example. That let's treat given college as a sample space or given city as a sample space. So there is this city and I'm treating that entire city as a sample space. Cool. And then in that city, I have some 10 institutes preparing students for, or some 5 institutes preparing students for GATE. And then I'm focusing at all the students who qualified GATE. I'm focusing at all the students who qualified GATE. So there is a city, and that city has certain aspirants who qualified GATE. Then there are certain aspirants who did not qualify the GATE. There are certain aspirants who qualified GATE, and there are certain aspirants who did not qualify the GATE. But these people who qualified GATE might have attended Institute A of that city, or these people who qualified GATE, some of these people might have attended Institute B of that city. Some of these people might have attended Institute C of that city. Some of these people might have attended Institute D of that city. And some of these institutes might have attended Institute E of that city. Okay, let me just save this and then remove this part. So just hold on a moment. So we have taken this sample space of a city, and in that we are defining an event that how many students qualified GATE. But these students who qualified GATE might be coming from Institute A or Institute B or Institute C or Institute D or Institute E. Okay, so someone who qualified GATE, someone who qualified GATE in a certain city, let's say Lucknow. In city of let's say Pune. Someone who qualified GATE in city of Pune might be from Institute A, Institute B, Institute C, Institute D, or Institute E. Cool. So how do we write the total probability of qualifying GATE? To write the total probability of qualifying GATE, I can naturally see that qualifying GATE is possible. Qualifying GATE is possible if you cover the intersection of. Qualifying GATE is possible in 5 different ways. And those 5 different ways are that qualifying GATE, some of the students belonging to Institute A also qualified GATE, and then some of the students belonging to Institute B also qualified GATE. So if I want to know that what is the chance of somebody qualifying GATE, then that chance may be fulfilled due to an student belonging to Institute A, or that chance may be fulfilled due to that student belonging to Institute B, or that chance may be fulfilled, by that student belonging to Institute C, or that chance may be fulfilled by that student belonging to Institute D, or maybe a student who qualified GATE happened to be from Institute E. Cool. So there are 5 different ways of satisfying this event called GATE qualified. There are 5 different ways of satisfying this event called GATE qualified or qualified GATE. Now, one way of satisfying this gate qualified or qualified gate is that you are going to say qualified gate and belonging to Institute A, or there is another way that somebody qualified gate and he belongs to B, or there is yet another way, and that another way is that somebody qualified gate and, my dear friends, that somebody belongs to Institute C, or there is one more way. This seems like a combined application of multiplication law and addition law, isn't it? This seems like a combined application of multiplication law of probability and addition law of probability. Or somebody qualified gate and he belongs to Institute D. Or somebody qualified gate and he belongs to Institute E. Or that's it. No or. Stop. No or. There is no or. So between the qualified gate event and between the event A, naturally there is some common area, and I'm interested in that. Between the qualified gate event that is represented by yellow boundary and that student happens from Institute A, there is some common area, and I'm interested in that much area only. So naturally, I'm writing qualified gate and intersection of A. Then there is or kept here, and then there is an event defined as qualified gate. Dhyan se samajhiyo. So this yellow boundary is defining the event of, or defining the collection of all such students who qualified gate in that city. All such students have been collected in this yellow boundary. But some of them, they come from different institutes. Some of them come from that white institute. Some of them come from green institute. Some of them come from the purple college. Some of them come from the blue college, and some of them come from the yellow college. My dear friends, naturally, I'm interested now in the common area between college B and the students who qualified gate. So that's the common area in which I'm interested. Or there is again the common area in which I'm interested, and that common area is the common area between qualified gate people belonging to Institute C, belonging to college C. So I'm interested in the common area between the event called qualified gate and the event called student coming from college C. My dear friends, next I'm interested in or the probability of a student qualifying gate can also be satisfied by choosing a qualified gate student who also happens to be from college D. Or the probability of someone qualifying gate can also be satisfied by choosing someone belonging to Institute E. So notice that this is again a combined application of question based on combined application of addition law of probability and multiplication law of probability. The only problem is that the multiplication law is not directly being applicable here, given that we are dealing with dependent events. Before I tell you what does that mean, let me simply break the or here by plus sign. Let me simply break the or here by plus sign. Let me simply write plus sign in place of or. You already know additional law of probability stands for or, union, or plus. Union means or means plus always. Intersection means and means product in most of the cases. So we have QG oblique QG intersection C, and then qualified gate coming from college D. And then there are students belonging to qualified gate category and belonging to college E. Cool. How do you write this? How do you write this one? This one you write like this. That. This one you write like this. That qualified gate, given that is coming from college A, multiplied by the probability of a student getting selected by college A. How do you express the second one? I told you make a note of previous topic. I told you make a note of previous topic, make a note of previous topic, make a note of previous topic. That B, I told you that B given A multiplied by PA can be written as B intersection A. A and A should be visible as getting cancelled. My dear friends, second one similarly we are going to break. Second one we are going to break one given another multiplied by another. So I can write this one qualified gate given that he belongs to college B multiplied by probability of a student belonging to college B. Probability of a student belonging to college B. Third one, qualified gate given that he belongs to college C multiplied by probability of someone belonging to college C plus probability of a student having qualified gate given that he comes from college D multiplied by the probability of someone belonging to college D, and then probability of qualifying gate given that the student belongs to college E multiplied by the probability of a student belonging to college E. Cool. This whole thing that you see in front of your eyes is called as computing total probability of an event which can be satisfied from different sectors. A, B, C, D, E are called sectors of the sample space. A, B, C, D, and E are called sectors of the sample space, are known by the name segments of the sample space, are known by the name fields of the sample space, are known by the name sub parts of the sample space. And one event might get satisfied from one part, another part, third part, fourth part, fifth part, sixth part. One event might get satisfied. Just think like geographically. Just think like you will think of a country geographically. That an honest person might come from the state of Maharashtra, an honest person might come from the state of Uttar Pradesh, an honest person might come from the state of Tamil Nadu, an honest person might come in from the state of Punjab, state of Haryana, state of Jharkhand, Chhattisgarh, Bengal, Bihar, and Northeast, and Odisha. All right, so if you are interested in getting the probability of an honest person, you say honest person given that the person is from UP and probability of the person being from UP plus. So basically this is called law of total probability, and this law of total probability is always applicable whenever a given event can be satisfied by a given event can be satisfied by following any one of the multiple sectors, any one of the multiple sectors. My dear friends, probability of qualifying gate can ultimately be written as probability of qualifying gate given that the student comes from college, the student comes from college I and multiplied by what is the probability of a student coming from college I. Of course, I is ranging from A to B to C to D to E. This final expression is known by the name the law of total probability. Make a note of this. You will need it, and you will need it a lot. We'll need it, and we'll need it multiple times. Olympic medalists of different countries. Exactly. There are so many examples. So many examples. Cool. So you can think of number of examples where this is going to be applicable. What is the probability of me enjoying at an Indian beach? What is the probability of me holidaying on an Indian beach? So you know that there are, if I say, what is the probability of a person being on a beach? Then you say somebody can be on a beach given that he's in Gujarat. Gujarat has beaches. What is the probability that he is currently in Gujarat? Then being at a beach can also be satisfied if you are in Maharashtra. Being at a beach can also be satisfied if you are in Maharashtra. Then what is the probability that the person is in Maharashtra right now? Being at a beach might be satisfied if the person is in Goa. Then what is the probability that the person is in Goa right now? Being at a beach might be satisfied if the person is from Karnataka. Then what is the probability that the person is actually from Karnataka? Being at a beach might be satisfied if the person is from Kerala. Then what is the probability that the person is actually from Kerala? Being at a beach might be satisfied if the person is currently in Tamil Nadu. And then what is the probability that the person is in Tamil Nadu? And then being at a beach might be satisfied if a person is in Andaman and Nicobar. And what is the probability that the person is in Andaman and Nicobar? Being at a beach is satisfied, can be satisfied if the person is in Andhra Pradesh. And then what is the probability that the person is in Andhra Pradesh? And then being at a beach. So now I'm feeling like going to beach and spending my evening today. If somebody is saying beaches so many times, naturally you will get that feeling. So my dear friends, being at a beach might be satisfied because you happen to be in Odisha. Then what is the probability that you happen to be in Odisha? And being at a beach might be satisfied if you happen to be in West Bengal. And what is the probability that you are currently in West Bengal? So basically, being at a beach is an event that can be satisfied from multiple sectors. And that's how you get this kind of scenario. That, of course, the whole sample space is India. And then your event that you are interested in That event is being at a beach. That event is being at a beach. Now, being at a beach, you might happen in Gujarat. Being at a beach, you might happen in Maharashtra, in Goa, in Karnataka, in Kerala, in Tamil Nadu, in Andhra Pradesh, in Odisha, in West Bengal. Cool. So might be Gujarat, might be Maharashtra, might be Goa, might be Karnataka, might be Kerala, might be Tamil Nadu, might be Andaman and Nicobar, might be Andhra Pradesh, might be Odisha, might be West Bengal. Being at a beach can be satisfied in so many different tariqas. We call them sectors. And then we write being at a beach. Being at a beach can be satisfied by the common elements between beach and Gujarat, or it can be satisfied by the common elements between beach and Maharashtra, common elements between beach and Maharashtra, or it can be satisfied by the common elements between two sets or two events. One is being at the beach, second is being in the Goa. I might be in Goa, but I might not be in the on the beach. You see, every state has not the beach also possible. Every state, if I'm in Gujarat, I may be at the beach, may not be at the beach. If I'm in Maharashtra, I may be at the beach, I may not be at a beach. If I'm in Goa also, I may be at a beach, I may not be at a beach. If I'm in Karnataka, I may be in Coorg, I may be in Sivasamudram, I may be in Hogenakal. No, Hogenakal is in Tamil Nadu. So if I'm in Karnataka, I may be in Coorg, but I may be in Mangalore, Udupi. If I'm in Kerala, I may be in, I forgot those tea valleys, or Munnar. I may be in Munnar, or I may be at a beach. In Tamil Nadu, I may be in, let's say, okay. So I may be at a beach or may not be at a beach. In Andaman and Nicobar, I may be at some, landscape, or maybe at a beach. In Andhra Pradesh, similarly, in Odisha, similarly, in West Bengal, similarly. But being at a beach can be satisfied by being in Gujarat. Being at a beach can be satisfied by being in Maharashtra. Being at a beach is having some common satisfaction with being in Goa. Being at a beach is having common satisfaction with being in Karnataka. Being at a beach has common satisfaction with being in Kerala. Being at a beach has common satisfaction with being in Tamil Nadu, like that, so on and so forth. Now, every OR connection, Goa probability will be highest, exactly. A person in Madhya Pradesh and enjoying at a beach, probability is 0. Exactly. So if you are going to define India and sectors like Madhya Pradesh, they will not have any common occurrence with that yellow space. If you define a sector like, Uttar Pradesh, that will not have any common occurrence with being at a beach. Similarly, if you define a sector like Jharkhand, it will not have any common occurrence with being at the beach. So being at the beach has a common occurrence with being in Gujarat. Being at a beach has a common occurrence with being in Maharashtra. Being at a beach has a common occurrence with being in Goa. Being at a beach has a common occurrence with being in Karnataka, like that. Now I use the formula that we developed in previous class, conditional probability. Conditional probability, I told you the formula already, that given that lambda, given mu, I can, if I multiply this with given that mu already happened, then only I get lambda, common occurrence of lambda and mu intersection. So from here, I can write being at a beach, given you happen to be in Gujarat, given that you happen to be in Gujarat, multiplied by probability of you happening in Gujarat, or means plus probability of being a beach, given that you are in Maharashtra, multiplied by probability of being in Maharashtra, probability of being at a beach, given that you are in Goa, multiplied by probability of you being in Goa, probability of you being in Goa, and so on and so forth. I can give it a symbolic representation that sum up being at a beach and then being in the respective state multiplied by probability of being in a state cancel hote hue dikhna chahiye, and of course the summation is going to be done for all such states. This is called law of total probability. This is known as the law of total probability. Okay, make a note of it. We are going to use it. We are going to need it multiple times. Of course, as of now, I have not used any numerical value. We'll be using numerical values, and we are going to solve some awesome problems based on this. Just make sure that you understand the law of total probability very well. Basically, law of total probability is used whenever an event defined in a sample space can get satisfied by co-occurring with any one of the multiple sectors. That event is happening because that event is happening with co-occurrence of sector 1, sector 2, sector 3, sector 4, sector 5, like that. Just
Sir,
one more problem.
actually here why are not using end conditions, sir? B intersection G and like that. Actually total no, sir.
Why are we not using?
End conditions, sir. B intersection G and before previous problem also, sir. Qualifying gate is total no, sir. We have to add all those.
No. Your event can be satisfied. I happen to be at a beach. There is only I. Can I happen to be at a beach simultaneously in a Gujarat beach and in Maharashtra beach?
No, sir.
Are we counting the people present on all the beaches? No. We are finding out the probability of one person being at a beach.
Okay.
So
sir.
that person can be at a beach either by being in Gujarat or by being in Maharashtra or by being in Goa or by being in Karnataka. One person cannot be at a beach while present in all states. Similarly, previous one, we call it law of total probability, not because of we are counting total number of people on beaches. No, that's not what we are doing. We are calculating probability of me being at a beach by totaling so many probabilities. That's why we call it law of total probability. Basically, total probability of an event is getting satisfied by satisfying from different sectors. Previous problem, gate qualified, also was similar. That if I select one mechanical engineer in that city, what is the probability that he is gate qualified? So I need to know that whether he's from college A, or he's from college B, or he's from college C, or he's from college D, or he's from college E. Or can one person be in a BTech program at two colleges simultaneously?
No, sir.
No. One person cannot be doing mechanical engineering in two colleges of a single city. I mean, there is no logic. Huh? Let me now take just one more example to help you understand the context where law of total probability will be used. Let me help you understand the context where the law of total probability will be used. Okay. And this time, let me take yet another field. Let's say we are taking the whole sample space hospital. And then we are defining the event of identifying a patient who has rashes on skin. Now, doctors in that hospital told me that sometimes people develop rashes just because of flu. And doctors also told me that sometimes people develop rashes, and in fact, they have very higher probability of developing rashes if they have measles. And sometimes someone might develop rashes just because of some medical allergy. Maybe he consumed wrong medicine. Or maybe food poisoning. Sometimes someone might develop rashes because of food poisoning. Sometimes someone might develop rashes because of sunburn. Food. So now, rashes on skin is an event that can be satisfied. Mind it, not every person who got flu develops rashes. No, not every person who got flu develops rashes. You see, there are people who have flu, and yet they have not developed any rashes on skin. This is the area that represents the people who caught flu and yet who are suffering from flu and yet they have not developed any rashes. But some people who caught flu might also develop rashes. Very few people who have got measles don't usually develop rashes. This area is representing the people who are measles positive, and yet they have not developed any rashes. But most of the chances are that if somebody has got measles, then rashes will be there. Many people, many people who have medicinal allergy from some kind of medicine or some kind of weather allergy or pollution or whatever, some kind of allergy, usually they don't develop any rashes. That's why we have so much area of allergic people in not rashes zone. But some people who have got allergy, also develop rashes. Some people who have got allergy also develop rashes. Okay. Some people who have got who encountered food poisoning, they don't develop rashes, but some others develop rashes on skin. Some others develop rashes on skin. So getting rashes on skin is satisfied being from multiple sectors. Similarly, having a sunburn, and there are fair chances of developing rashes on skin. Cool. And then there is a fair chance that no rashes have been developed. Cool. So if I just want to randomly select a patient, what is the probability that he has rashes? If I select a person randomly, what is the probability that the person has got rashes on his skin? What is the probability that the person has got rashes on skin? The person has got rashes on his skin can be, as I said, can be satisfied by simultaneous occurrence of flu. So maybe it can be satisfied by the common element of rashes and flu, or maybe that person is having rashes and he has got measles. Maybe that person got rashes and also got measles. Maybe that person got rashes and got allergy. So there is one more mutually exclusive way of getting rashes, or maybe that person got rashes and at the same time he got some allergy. Maybe, or once again there is or. Why or? Because maybe he got rashes due to food poisoning. So maybe he got rashes due to food poisoning, or maybe finally the person got rashes due to sunburn. My dear friends, this is a beautiful application of combined application of addition law of probability and multiplication law of probability. Multiplication law, not usual one, but the conditional probability wala. Multiplication law here we are using not the usual one, but the one that we used at the time of conditional probability. At the time of conditional probability, rashes and flu, rashes and measles, rashes and allergy, rashes and food poisoning, rashes and sunburn. My dear friends, now you are going to use lambda given mu multiplied by probability of mu is equal to lambda intersection mu. Lambda intersection mu. So you can again write rashes given flu multiplied by the probability of developing flu. R means what? R means plus, and then rashes given measles multiplied by probability that someone has got measles. That you can calculate, huh? R means plus, rashes given allergy, and then what is the probability that somebody got allergy? What is the probability that somebody got allergy? This area divided by this area divided by total. That is the probability of a person got allergy. Rashes given food poisoning, multiplied by probability that a person is suffering from food poisoning, raises that there is sunburn that happened, multiplied by the probability of sunburn. Once again, if an event can be satisfied in different sectors of a sample space, different sectors of sample space, then the randomly drawn object will be belonging to that event can be written using conditional probabilities of various sectors. This final statement is known as the law of total probability. This final statement is known as the law of total probability. इस final statement को कहते हैं the law of total probability. All right, let us finally use enough understanding the law of total probability. Now, before we go ahead and start solving a problem, just one last time I redefine the law of total probability that you might be having an event defined in a sample space, then that event might get satisfied. That event might get satisfied either from sector A1 or from sector A2 or from sector A3 or from sector A4 or from sector A5. You're defining an event, and that event is event E, and that event E might be satisfied either by satisfying A1, A2, A3, A4, A5. Exactly. I'm sorry. I got distracted by a very important message. Then the probability of event E being satisfied can be satisfied either given that sector A1 happened, multiplied by probability of sector A1 itself, and so on and so forth. This is called, one last time, the law of total probability. E given AI multiplied by probability of sector AI. And let us now solve some problems. College A has 1800 students. College B has 2000 students. Out of 1800 students, College A has 1300 students belonging to science stream and 500 students belonging to arts stream. Out of 2000 students, College B has 1100 students belonging to science stream, and my dear friends, 900 students belonging to arts stream. 1100 students belonging to science stream and 900 students belonging to arts stream. out of 2000 students present in a college, college B. Now suppose the whole city has only these two colleges. For the purpose of simplification, I'm considering that we have only these two colleges. For the purpose of simplification, I'm considering that we have only these two colleges, College A and College B. College A and College B basically define the whole sample space. The whole sample space consists of only these two colleges, A and B. And all of a sudden, I ask this question to a student that you belong to science stream or you belong to arts stream. And the person says, I belong to arts stream. What's the probability that if the person belongs to arts, then he happens to be from college B? What's the probability that if the person belongs to arts, given that the person belongs to arts, what's the probability of him being from college B? What's the probability? You understand what is being asked here? That what is the probability of being from college B given that someone accepted that he's from arts stream? If someone says he's in arts, what's the probability that he would be from college B? Now you see, naturally, generally, when we start conditional probability, we always think of a sequence, a logical sequence. We said, given that it is odd number, it will be 1. What is the probability? We said, given that it's a colored marble, what is the probability that it will be green 1? We said, we always say something happening previously first, and then we say something that is logically the next thing. We say that a defective screw already drawn, then what is the probability of that screw to be undersized? Now, if I say somebody belonging to college A, what is the probability of that somebody belonging to arts if he is from college A? You will calculate it so easily. You'll calculate it so easily. You'll say 500 upon 1800. If I ask you what is the probability of arts given that somebody is in college B, you will calculate it so easily. You'll calculate it 900 divided by 2000. But I'm asking it reverse manner. Now this is called posterior probability. Okay? That sometimes we know the results and we need to fix the causation, that what might have caused this result. If somebody belonging to arts is the result, there are two causes. There are two possible causes, college A and college B. So which cause produced that effect? I'm interested in that. These two things are obviously very easy, but we are not interested in these two things. Now we are interested in opposite thing, that if somebody happens to be in arts, what is the probability that he came from college A? If somebody happens to be in arts, what is the probability that he belongs to college B? Cool. If somebody happens to be from arts, what is the probability that is belonging from college B? My dear friends, naturally calculating these kind of probabilities is directly not possible. So what we do rather, we change it into opposite thing. College B given arts. College B given arts. multiplied by probability of being from arts is equal to arts, given that somebody belongs to college B, multiplied by probability of someone belonging to college B. Now I'm interested in this weird probability. Weird probability that what is the probability of somebody belonging to college B, given that he is in arts, is equal to probability of being in arts, given that person belongs to college B, multiplied by probability of the person belonging to college B, and this divided by probability of person being from arts. Now, just one last step and we are done. And that last step is written at the top of this page. That a being from arts can be satisfied. Being from arts can be satisfied in different sectors of the city. A being from arts can be satisfied by being from college A and also by being from college B. Then we are going to use the law of total probability. Being from arts can be satisfied in different sectors of the city. I'm going to use the law of total probability. Arts given A multiplied by A, arts given B multiplied by B. So college, what is the probability that if somebody belongs to arts, what is the probability that he is in college B? Then arts given that college B is having 900 upon 2000 chances. 900 upon 2000 chances, and somebody being from college B has chances 2000 upon 3800 divided by arts given college A multiplied by college A given college A plus arts given college B multiplied by probability of being from college B. Calculate this and be happy. Something that you are doing right now is the Bayes theorem. Something that you are doing right now is Bayes theorem. Do it, people. Calculate it. Tell me what exactly are you getting. Somebody calculated? Tell me, guys.
0.6428, sir.
0.6428. Cool. We'll solve multiple problems back to back like this. as a 27th problem. Let's say there is an interview going on. And in that interview, "60 computer engineers arrived and 42 mechanical engineers arrived. Out of 60 computer science engineers, there are 63% who are good at Java. And out of 42 mechanical engineers, there are 56% who are good at Java." The programming language. 63% know Java very well. And out of the 42 mechanical engineers who have appeared, 56% know Java very well. And now, one person, I'm not looking at the profile of the person, one person just appears, one person just enters into the interview panel, interview hall. And I asked, the first question I asked to him, "You know Java?" He says yes. What's the probability that he is a mechanical engineer? Now, this is posterior. I know the later thing first. What is the probability of arising from one cause or another cause? Arising from one cause, one sector or another sector. Okay. So this is called posterior, and Bayesian theorem, Bayes theorem is such a beautiful thing in this case. Cool. So if a person, what is the probability of the person being a mechanical engineer given that he said he knows Java? Now, unfortunately, you can't solve this problem directly. You'll have to use Bayes theorem. You'll have to use Bayes theorem, and we'll use Bayes theorem just like previous problem. Exactly like previous problem. Given that the person knows Java, what's the probability that the person belongs to mechanical engineering? Multiplied by the person knowing Java is equal to, what is the probability of knowing Java given that the person is a mechanical engineer? Given that the person is a mechanical engineer, multiplied by probability of a person being mechanical engineer. I'm interested in this one, that if the person knows Java, what is the probability of being a mechanical engineer is equal to the probability of knowing Java if the person is mechanical engineer multiplied by probability of a person being a mechanical engineer divided by the total probability of the person knowing Java. Now, one last step, and that last step will be written by the law of total probability. Probability of being a mechanical engineer given that the person is knowing Java is equal to the probability of knowing Java given that the person is a mechanical engineer multiplied by the probability of the person being a mechanical engineer divided by the total probability of Java can be broken into, because being a knowledgeable at Java can be satisfied from two different sectors. Having knowledge, having command over Java can be satisfied from two different sectors. It can be satisfied because the person belongs to CS, and then what is the chances of belonging to CS? Plus a person knowing Java given that he is mechanical engineer multiplied by the probability of being a mechanical engineer. My dear friends, you can actually put all the values are given. You can put them and solve this beautiful thing. So let's put all these values. What is the probability of knowing Java given that someone is mechanical engineer? That probability is given to you, 0.56. That probability is already given to you, 0.56. And what is the probability of a candidate belonging to mechanical engineering? The probability of a candidate belonging to mechanical engineering is 42 upon 102. Probability of having command over Java, given that the person belongs to CS, that probability is given to you, 0.63. And what is the probability that the person belongs to CS? The probability that the person belongs to CS is 60 upon 102. Out of total 102 candidates, 60 of them belong to CS. Then the same thing that you have written in numerator will be repeated here. You solve this and tell me if somebody claims that he knows Java, what's the probability that the person is a mechanical engineer? Such lovely problems can be formulated from so many, fascinating areas. Now, think about this whole setup. This setup, I've not taken from any book or something. This setup is just like I thought about that scenario. And oh, let's say an interview is going on and let's define two sectors. One sector is mechanical and one sector is CS. And then there is one event that can be satisfied from both the sectors. And that event is commanding the programming language Java. So I divide the whole thing into two sectors: computer science, mechanical. And there is one event that can be satisfied from both the sectors. And that event is commanding Java. Okay, let's move ahead and let's move ahead and do the next problem.
0.3835, sir.
Point
3835.
0.3835 is the answer. Perfect. Moving on to the next one. Moving on to the next one. So as a 28 problem, let's say in a hospital, let's simplify the things. In a hospital, 65% patients have flu and 35% patients have measles. Out of the 65% people developing flu, 32% have the chances of rashes. Whereas out of the 35% people having measles, 84% develop rashes. So now rashes is an event that can be satisfied from two sectors. Rashes is an event that can be satisfied from two areas. And these two areas are flu and measles. These two areas are flu and measles. So developing rashes is a common event, and that developing rashes can be satisfied either by having flu or by having measles. This yellow circle is defining the event of developing rhesus. Now suppose I see one patient and I find that he has got rhesus on his skin. Now suppose I see one patient and then I see that the person has got rhesus. What is the probability that the person has measles? This is called posterior. Looking at the root cause, finding the probability of a root cause, given that some symptom has already appeared. Finding the probability of whether that symptom or that after effect is arising due to cause 1, or that after effect is arising due to cause 2, or that after effect is arising due to cause 3, or that after effect is arising due to cause 4, or cause 5, or cause 6, or cause 7. Cool. All right. Keep in mind that this is 100% okay. The flu and the measles define the whole sample space that is in consideration. All right. And out of the space of flu, then we further have 68% not developing rhesus and 32% developing rhesus. Out of every person, out of the persons having measles, only 16% have not developed rhesus. Remaining 84% have developed rhesus. Of course, area is not representing that kind of feeling here, but it's okay. भावनाओं को समझो. So what is the probability that if a person has, given that a person has rhesus, what is the probability that the person has got measles? Once again, the strategy that we used in previous problem, measles given rhesus multiplied by probability of rhesus is equal to rhesus given measles multiplied by the probability of measles. Rhesus given measles multiplied by the probability of measles. Now, my dear friends, I'm interested in measles. I'm interested in measles given rhesus. Measles given rhesus. So I'm going to write rhesus given measles multiplied by probability of measles divided by probability of rhesus. Probability of rhesus. Now, let us write the denominator of this using law of total probability. Rhesus given measles multiplied by probability of measles divided by, how do you write the total probability of, how do you write the probability of rhesus, given that rhesus can be satisfied by satisfying two sectors. One is flu, another is measles. Rhesus given measles multiplied by probability of measles plus rhesus given flu multiplied by probability of flu. Let's put all the values. What is the probability given measles are there? That probability is 0.84. And what is the probability of a patient having measles? That is 0.35 divided by Rhesus given measles is 0.84 and measles is 0.35. And rhesus, given that flu is rhesus, given that the person is suffering from flu, that probability is very small, 0.32 only. And what is the probability of person suffering from flu? That probability is high. Out of 100, 65 people are suffering from flu. So you notice these are some coolest problems of probability. These are some behatareen problems of probability. Some awesome problems of probability. Okay, let me know the answer. What exactly are you getting?
Point 58565.
0.58565. Percent. Thanks, people. We are done with probability. Tomorrow we are going to start probability distributions.